So part one set the stage, part two defined the problem. It's finally time to bring it home. How do we take these optimization problems that we set up in part two and actually find a way of solving them? So we found a way of phrasing these, finding a polynomial of a particular degree that best fits a set of points with respect to a particular norm, the L1, the L2, or the L infinity norm. We found a way of turning that into an optimization problem. In fact, we found a couple of ways. We found a way of stating it as unconstrained or as a constrained optimization problem. But in part two, we weren't able to find a way of turning it into a linear problem. So the first question is, here is the L1 regression problem. You may notice the change in terminology. I'm going to call this problem the regression problem, not just curve fitting. It is the specific case that we would use for L1 for regression. So here is the L1 regression problem written in its constrained form. I want to minimize the absolute value of each of these error terms, subject to a constraint system that essentially serves only to make sure that the error term is defined correctly, to make sure that the error is indeed defined to be the value of the polynomial minus the actual y value at that point. So we want to find a way of writing this as a linear program. Maybe it's visible from inspection that the only real problem with it is the absolute value symbol. All of the other stuff that seems nonlinear, so the fact that I'm taking xm squared, that's not a big deal because the optimization variables here are my coefficients, C0, C1 up to Cn, and the epsilons. The value x2 the value xm is actually a constant, and therefore I can square it all I want because it's just an input to my problem. I just pre-compute the square of xm. So find a way of turning this into a linear program. And the slides, somewhat belatedly here, are pointing out, yeah, the only problem is this absolute value symbol. What do we do? So the absolute value symbol is not strictly a linear thing, although there are reasons to believe that there might be some hope. So if we consider the sketch of the absolute value function, it does look like it's got some linear influences, certainly. It isn't linear, but it has some linear influences. Maybe there's something we can do that allows us to use absolute values in linear programs. One option would be to see if we can juggle stuff until the absolute value symbol becomes more palatable. So what we could do is we could peel off the absolute value symbol from the objective function and just move it over so that we define epsilon 1 to be the result after taking the absolute value of the error. But that doesn't really fix the problem because all it really does is moves the absolute value symbol to the constraint system. And it has the effect of forcing each epsilon to be non-negative because obviously the epsilon is now being computed after the absolute value instead of before it. On the other hand, there is this nice trick we can use. I think it's a technique you'd call a gadget, I guess, because it's a device you can plug into a linear program to turn an absolute value symbol into a linear constraint. And it's this. So the claim is, if you give me a constraint that looks like this, p is greater than or equal to the absolute value of q, it turns out, the claim at least, is that that's equivalent to this pair of constraints, both of which are linear. Additionally, if you give me an optimization problem where I am expected to minimize p, and p has to equal the absolute value of q, that as long as no other constraints are acting on p besides this one, I can actually replace it with this. I can use the same substitution. And I want to sort of go in reverse order for justifying this. So why is it that I can go from this to this? And the idea is if I'm minimizing p, then this is actually equivalent to this formulation here. Minimize p subject to p is greater than or equal to the absolute value of q. I can actually relax that equality sign. And the reason I can do that is, for this specific example where I am minimizing p, it doesn't make any sense that if no other constraints are acting on p, when would I end up with an optimal solution where p was greater than the absolute value of q? It makes no sense. Because obviously, if p is supposed to be greater than or equal to the absolute value of q, which is always greater than or equal to 0, so this constraint doesn't get in the way. If p is always supposed to be greater than or equal to the absolute value of q, and suppose the absolute value of q ended up being 5, why would p ever be 6? Why would there ever be an optimal solution? If p is supposed to be as small as possible, why wouldn't it be locked into equality with the absolute value of q? That's the basic justification of this step here. So because no other constraints are acting on p, I don't actually have to think about this like an equality symbol. I can instead think of it like a greater than or equal to sign. Okay, then I go back up here. This constraint, p is greater than or equal to absolute value of q. Okay, so wait a minute. What is the absolute value of a number? If the value is positive, the absolute value is just the number itself. If the value is negative, so for example, the absolute value of -5 is going to be equal to 5. Okay, but how do I think? I mean, yeah, fair enough. But I could also think about that as the absolute value of -5 is -5. I have to use a negative sign to cancel out the existing negative in the number. In other words, if I take the absolute value of an arbitrary number, it will probably be the largest of these. So if I consider the absolute value of q is equal to the maximum of the following two values. It's either q or -q. One of those is bigger, and the bigger one will be the positive one, and that will be the absolute value. Although it's interesting how my use of a max operator might be helpful on the assignment, in fact. It turns out that if I have a situation like this, a discrete max operator, I can just split it up into a bunch of constraints. If I want p to be greater than or equal to the larger of q and -q, I'll just add two constraints. And I'll know that whichever one is larger, whichever of q and -q is larger, will be the constraint that is met most tightly. And so in this way, I can, in the case where I have a greater than or equal to constraint, I can actually encode an absolute value into a bunch of linear constraints. And furthermore, if I have an equality constraint and I'm minimizing, the equality constraint decays to a greater than or equal to constraint, and so I can apply this as well. And so I now actually have enough, because of the specifics of this problem, because I'm minimizing each epsilon. Each epsilon is defined to be an absolute value, but otherwise has no other constraints acting on it. I can use these insights to turn this into a linear program. Here is a textual justification of what I just said, but because I just said it, you can just read the slides later if you want to. So I can use that transformation to turn this thing into a linear program, and it's going to be ugly. There it is. So I first converted the linear program to this notation where all of the absolute values were in the constraint system, and then I applied the transformation to double up constraints. And we're familiar already that there are transformations we do, for example, to put things in standard form that require doubling up of constraints. And although, yes, it's no fun to the solver to have more constraints to work with, it is a perfectly healthy transformation to have to perform. And so I do this. And then, obviously, the result that I get, because I had to apply the transformation on a greater than or equal to sign, the result that I end up with doesn't look like it's in standard form, but of course, I can convert it to be in standard form. And I get this. And my optimization variables here are the epsilons and the c's. And we'll notice that because the epsilons are defined by equality constraints, really, they're only there as proxy variables anyway. The things I care about are the coefficients C0 to Cn. And so I get this. And so I've been able to perform L1 regression, minimizing the L1 norm using a linear program, even though L1 norms themselves are defined using apparently nonlinear things. What about L2 regression? So this would be least squares regression. So it's the form of regression you are most likely already acquainted with. And you might want to take a moment to look back and think, are there times you've used least squares regression where it truly was the best choice for the task versus, let's say, L1 regression, or the one you used because it seemed to be the easiest one to compute? There might be, just like how in many cases, people use the mean to estimate a set of data because they don't know any better. There might be a lot of cases where you might use least squares regression in cases where L1 regression might work better, because when you were taught regression, you were only taught how to solve least squares regression, because the alternative would require knowing linear programming, which you probably didn't learn until this course. So either way, we know how to solve L1 regression. We should figure out how to solve L2 regression so we have all of our options at our disposal. Is there a way of solving this? Well, okay, yeah, we could. We could solve it with quadratic programming. The objective function is quadratic, but that's it. That's the only nonlinearity. And there are quadratic programming solvers out there. We could use those. There isn't a way of converting this to a linear program. But strangely, in a sort of bizarre inversion, there is a way of computing the solution without any kind of optimization algorithm. We can just use linear algebra directly. And the way that we do it is basically going back to what I did in part 1 with computing the mean, with proving that the mean minimized the sum of squared errors. We leverage the fact that the derivative of a quadratic function is going to be linear, and therefore we can apply linear techniques. And so the way we're going to solve the L2 regression problem is is in fact just using straight up linear algebra. So here is the unconstrained version of the L2 regression problem. We did write it out in a constrained way before, but we'll actually get more mileage out of solving it if we go back to the unconstrained form. So this is the objective function. We'll call it f of c1 to cn. So how do I find the global minimum of this? Notice that this function is in fact a continuous function defined everywhere and in fact differentiable everywhere. And so I could solve it using the usual method for unconstrained optimization. What I could do is I could find points where the gradient equals 0. Now, we could say a bunch of other stuff about this function to decide how many such points exist, but it turns out in our derivation we will determine that we can basically find the global minimum because only one such point can exist. So the gradient of my function f will be the collection of partial derivatives. And what I want to do is find places where the gradient of f itself is equal to the 0 vector, which means every single partial derivative equals 0. The way I'm going to unpack this on the next few slides is I'm going to talk about a specific partial derivative. So let's say the partial derivative of f with respect to one of my coefficients. And then I'll show what happens if we set that to 0. And eventually we'll wrap that back up and show how we can compute points, sets of coefficients where the whole gradient equals 0. So each individual partial derivative, if I take the partial derivative with respect to a particular coefficient ck, I will get, so I'm taking the derivative of this with respect to ck, it turns out that I get this thing. Notice that this thing does involve the other coefficients. There's a sum here that goes through all of the coefficients, C0, C1 up to Cn. And that's because I'm taking the derivative with respect to Ck, but Ck appears inside this term that gets squared. And so we can expect that the terms inside that are underneath the square there will survive in the derivative. They won't get eliminated. And that's why I end up with this sort of ugly, but actually linear derivative. All the nonlinear stuff involves the x values, which of course are constants. There's nothing nonlinear with respect to my coefficients Cj. So each individual partial derivative is an expression of this form here, the derivative with respect to ck. What I want to do now is figure out where are the points with respect to my coefficient c where each of these partial derivatives equals 0. Before I talk about all partial derivatives, I'm going to continue talking about this individual one and do some rearrangement. So if I set this partial derivative to equal 0, and then I rearrange terms for a while, I end up at this. This is something, like I said earlier, I am not going to belabor the tedious algebra that gets in the way here. We're so good at rearranging sums in this course that I don't think we need it, but you're welcome to try that out yourself. We can talk about it in the office hours too. Basically though, if I set the partial derivative, this partial derivative, the one I was already working with, to 0, it is equal to 0 at collections of coefficients where this relationship holds. And if we stare at this for a while, it might be sort of clear from the double summation and this other summation that maybe we're looking at something that might be relevant to matrices. But certainly we notice that this appears to define a system of equations. And it turns out if I consider the collection of all partial derivatives, that I will get a system of n+1 equations in n+1 unknowns. So why n+1? Well, because if I'm deriving a polynomial of degree n, there are n+1 coefficients, because there's going to be a coefficient on the x to the 0 term. All right, so what I want to do now is try and figure out if there's any logic to these weird-looking sums. So I've got a double summation on one side, which does, to me, ring some bells as far as matrix multiplication is concerned. I really wish there were a derivation where we could sort of unpack a matrix directly out of this sum, but I have to sort of shirk that a little bit and say, no, I'm going to just pull a matrix out of thin air magically, and then explain to you how this matrix ends up being relevant. So here's a matrix. Notice that it looks very similar to that matrix we derived earlier for polynomial interpolation. It is the set of powers of each x of each of the x values that I was given. So here's xi to the 0, here's xi to the 1, here's xi to the 2. Each column is a particular power of every single x coordinate. First observation. If I go back to this form here, when I'm looking at one of my partial derivatives, I've got this right-hand side, which seems to be the most friendly of the two sides, so we'll start with that. First observation. It turns out that this sum, if you squint at it a bit, is actually the kth entry of this product here, this matrix vector product. So the matrix I just defined, this matrix A, has one column for each power. So column I will be the ith power of each of the different x coordinates. If I take the transpose of that matrix, AT, then each row will be one power. So row 0 would be x to the 0, row 1 would be x to the 1, and so on. What I observe from this sum is going to end up equaling, let's see, so it'll be x1 to the k times y1 plus x2 to the k times y2. And all the way up to xm to the k times ym. Notice that the power that I'm taking remains the same the whole time. It's always k. And therefore, if I try and separate this out into the a dot product, because maybe it's clear this sum looks a lot like a dot product, I end up with the following dot product. x1 to the k, x2 to the k, and so on up to xm to the k, dot y1 up to ym. Maybe you can satisfy yourself that the product of this matrix and this vector will itself be a vector, and the specific element of the vector that will equal this sum will be the product of row k of the matrix, which would be this thing, multiplied by the vector y. That's where I'm getting that from. So this particular sum is one element of the product of this matrix and this vector. And I know it seems confusing that I'm only talking about one element, but I'm talking about matrices and vectors. The key thing to observe is when I derived this thing back here, I was talking about one partial derivative, the derivative with respect to c sub k. I want to eventually have a form that talks about all partial derivatives. And so here I've noticed that for a particular partial derivative, ck, I'm looking at one entry of this matrix product. But if I'm talking about all partial derivatives, I will be talking about the entire matrix product. So that's observation 1. The right-hand side of this expansion is one of the entries of the product AT times Y. I've also noticed, sorry about this, these are vectors. Y is a vector, so it should be bold-faced. I'll try and change that in the posted version of the slides. Observation 2. This pretty unfriendly fellow here is actually also can be explained in terms of our matrix A and a vector of coefficients, this vector here, we'll call this vector C. It's a little bit less obvious to figure out exactly what's going on here. I have a slide that tries to unpack it a bit, but because it essentially is just tedious algebra, your mileage may vary on whether the slide I'm about to show will really help. But it turns out that this sum here is one entry of the following large matrix vector product. The result of this, the result of this will be a vector. So this particular sum will be the kth entry of that vector. Okay, so why is that? Like, where am I getting this from? Well, first, I'm going to begin by trying to take apart the matrix ATA. So A transpose times A. We'll call that matrix Q. Okay, so Q, which is equal to A transpose times A, will be an n plus 1 by n plus 1 matrix. And because of the way matrix multiplication works, each individual entry of Q will be equal to this thing. Okay, now if I try and compute, as I'm doing back here, I'm trying to compute the product Q times C, we'll call that R for the sake of the example. If I'm trying to compute Q times C, then applying the same law of matrix multiplication, I should end up with this. So there's some pretty ugly LaTeX here. I'll try and rewrite that. And in handwriting, it'll be even uglier, but it will be correct. So each element of the product will equal the sum as j goes from 0 up to n of qkj times cj. And because we know what qkj is, we can just sub that in. And if we do that, we end up with this expression, and then if we remove brackets, we end up with this expression. Notice that that matches our friend from a minute ago. That's where I got it from. I know that that doesn't really tell you anything about the underlying mystical qualities of the sum, but I hope you agree that does explain where I got the sum from. The slide is also saying, hey, you might be noticing all these zeros here. And you might be wondering, hey, has Bill forgotten to use 1 again? Because he's done that in previous slides. This is actually deliberate. Don't worry, despite evidence to the contrary, I did proofread this stuff. The reason that the indexing over j starts at 0 is that I'm using the indexing, the J indexing is referring to the same indices that I'm using for my coefficients. And remember that there is a coefficient, my eventual polynomial will be C0 plus C1 times X1 plus C2 times X2, all the way up to Cnx to the n. And that means that there are going to be n plus 1 coefficients. And because I don't want to do a weird indexing adjustment where I go from 1 up to n plus 1, because there is actually a coefficient numbered C0, my index j will start at 0. So that is deliberate, I get it. I know there are other typos. There are so many other typos, but that isn't one of them. Okay, so if we combine all of those observations, the two observations were saying what, if I'm talking about one particular partial derivative, what it means to set that to 0. Well, what it means is, in this case, that for the partial derivative of f with respect to ck, for that to equal 0, well, I end up with this has to equal this. And we know that the thing on the right is one entry of this one product, and the thing on the left is one entry of this other product. And so that means if I want all of the partial derivatives to equal 0 at once, I want the entire matrix and vector product on the left to equal the entire matrix and vector product on the right. And that means that if I want a set of coefficients that sets the gradient to 0, I just need to find a vector c that meets this criteria, keeping in mind that the matrix A and the vector y are all constant. I can compute those using only the input points that you gave me. The only unknown here is c. And just to contextualize that further, if I want the value of c, what should I do? Well, let's see. So, okay, we know that A transpose A multiplied by c is going to be, for the vector that I want c, A transpose A times c will equal A transpose times y. So all I need to do really is solve this for c. And I mean, this is a matrix, so what I could do is I could try multiplying both sides by the linear algebraic inverse of A transpose A. So I end up with this. And then this and this cancel each other out, and so I end up with C equals this. Now, it's worth noting that if you actually wanted to compute C in practice, you probably should not compute the inverse of this matrix. I'll talk about this in next week's lecture, but you may know this from numerical analysis. If you can avoid it, never ever compute a matrix inverse. Instead, try and solve systems of equations. There is a way of computing the vector C without actually inverting any matrix, assuming the matrix is invertible. So that's a big assumption, and I'll talk about that one in a minute. There is a way of actually getting the value of C without doing any matrix inverses by instead solving a bunch of equations, by basically performing Gaussian elimination over and over again. I can lay that out briefly. So let's do this. So we'll define Q equals A transpose A. So now I want to solve the system Q times C equals A transpose Y. So I want to find a vector C such that this holds. Well, notice that A transpose and Y are just constants. And so why don't I define a vector V to equal A transpose Y? So what I really want is to solve this equation. Q times C equals V. I compute the matrix Q, I compute the vector V, and then I do Gaussian elimination or whatever the hell I want to compute C, to solve the system. I do not have to invert stuff. And I'll talk next week about this. Inverting matrices numerically is a bad idea. You should try to avoid it basically whenever you can. Solve systems of equations instead. And not only is it usually faster, it also can save you a whole world of hurt in terms of weird numerical stuff that can happen. But there's this. We don't like, in this course, I really don't like, assume the matrix is invertible. Yeah, I don't like that. So when is the matrix invertible? I feel like this is important to talk about. This is getting a little bit tangential, but I will talk about it. I want to go through the most basic justification of why it's invertible. So I'm going to cut a few corners because I only want to prove that this particular matrix A transpose A, so if I define A to be this, that this is going to be invertible under basic assumptions. But I feel like this lecture will not be complete unless I explain that it's reasonable to assume that A transpose A is invertible. So I'll go over this briefly. I'm also going to try and go over it with terms without requiring too much advanced linear algebra. There are a couple of tricks we can use here that would make it faster. First one, this is a lemma that I have pruned down to be basically specific to the case we're working in. It turns out a lot of these constants I'm dealing with here, I can relax a lot of these requirements. But for the sake of only using the assumptions we've already made, I can write it like this. So the matrix A, the columns of the matrix A are these things. Earlier, we all agreed, me and the 0 other people in the room with me right now, we all agreed that it's reasonable to assume that the x values of all of our input points are distinct. So that's why I say, look, let's say we have m distinct x values. And frankly, the word at least makes no difference. It turns out you don't even need m of them, but I'm going to say m of them for the sake of this justification. It turns out that if you have that, then all of the columns of A are linearly independent. And that means that A has rank n plus 1. And that also relies on this assumption here. I hope you remember what rank is from a linear algebra course. The way I'm going to prove that A transpose A is invertible is by showing that it also has full rank, which is rank n plus 1. That is sufficient to show that a matrix is invertible. So the first step is the matrix A is invertible. The matrix A has linearly independent columns. It has full rank. Actually, I should be careful. The matrix A has rank n plus 1. A itself might be rectangular, so it may not be invertible, but A has rank n plus 1. And that's because the set of columns I defined is linearly independent. Okay, that's lemma number 1. The second lemma is that the rank, and this turns out to be true in general, but I only really care about it for this one case. The rank of A transpose A happens to be equal to the rank of A. And this is just the general justification, but just keep this in mind that I don't intend to present a general case. It just turns out that it's easier to do this. So if A is m by n plus 1, as it is in this case, then A transpose A will be, by the basic rules of matrix multiplication, n plus 1 by n plus 1. Both of the matrices actually have the same number of columns, as I'm sure you can observe. So obviously this is the number of columns, n plus 1 columns in both matrices. Since both matrices have the same number of columns, we can actually write the rank of each matrix using relatively similar terminology. So we can say, well, the rank of A will equal the dimension of the null space of A, which we typically denote by the term nullity of A, subtracted off from the number of columns. And what we're ultimately trying to prove here is that this dimension is small, that the null space of A doesn't really contain anything. So the rank of A is n plus 1 minus the size of the null space. The rank of A transpose A is expressed the same way, just in terms of the null space of A transpose A. What I would like to do is to prove that the size of the null space of A happens to equal the size of the null space of A transpose A. Because if that's the case, if this equals this, and I know that the rank of A equals n plus 1, then of course that means that this has to equal 0, and that this has to equal 0. And that'll be enough to prove that the rank of A transpose A is equal to n plus 1, which means A transpose A is a square matrix with full rank, which means it's invertible. So the way I'm going to prove that is by showing that the null space of A is actually the same as the null space of A transpose A, and I'll do that in two ways. So first, I'll show that anything that is in the null space of A happens to be in the null space of A transpose A. I guess I'm late to the party here, but just in case, the null space of a matrix is the set of all vectors such that the set of all vectors x such that A times x is equal to 0. That's what I'm trying to show, is that if I multiply, if I have a vector such that A times x equals 0, then A transpose A times x equals 0. So the first thing is, if if A times x equals 0, well then A transpose A times x by associativity would be A transpose times A times x. But we know that A times x equals 0, and therefore this is going to end up equaling 0. A matrix times the 0 vector equals the 0 vector. Therefore, the vector x has to be in the null space of A transpose A. Okay, that's part 1. Part 2 is just to show the other direction of this, to show anything in the null space of A transpose A is also in the null space of A. This is a proof that I have shamelessly taken from somewhere else. The reason I have no shame is that it isn't plagiarism as long as I give a citation. I think I'll include a link to this in the notes that accompany the video. So I want to show that anything in the null space of A transpose A has to be in the null space of A. This is a case where I went looking for a concise proof of this that didn't sort of go all over the place or need advanced stuff, and Wikipedia had this really clever one that I thought is worth seeing for so many different reasons. So let's consider some vector x in the null space of A transpose A. Well, then we know the following. We know that A transpose A all times X has to equal 0. That's the definition of the null space. And so what I'll do is I will multiply both sides by X transpose. And we can verify, I don't want to get into the weeds with this, but it turns out that that is a valid thing to do. It turns out that the dimension of the vector I get on both sides is such that I'm allowed to do that because the matrix is square. And X is therefore a vector with n plus 1 elements, which means that I can take A X transpose multiplied by the vector that comes out of this. So I do that. So I end up with this expression here. I know that A transpose A all times X is 0, which means X transpose A times X equals X transpose times 0. And then I take a look at what I have on both sides. Okay, so the first thing is I guess, ominously put brackets around X transpose A transpose, and I'm going to observe that this is actually a dot product. We've seen already, for example, we've seen linear programs where we're taking minimize C transpose X, which is the same as C dot product X. We know that if I'm multiplying to X transpose times the 0 vector, this is just going to be a single number. It's going to be a dot product. It's going to be a scalar. So this just equals the scalar value 0. Over on the left, I have X transpose A transpose. And by the laws of matrix multiplication and transposes, when I have something like B transpose A transpose in brackets, that is just equal to A times B all transposed. And so I apply that transformation in reverse. So X transpose A transpose just equals AX all transpose. And then I stare at what I'm looking at here. So I'm going to rewrite it so that I can draw all over it. I've got more resolution to draw on. So I've got this. And I have to ask myself, I guess philosophically, what exactly is A times X? So A times X is a vector, because X is a vector. So X times A will also be a vector. In fact, it'll be a vector of n plus 1 elements. And A times X is, of course, also a vector over here. So what I have, in a sense, is a vector transpose times itself. In other words, I've got another dot product. So I've got AX dot product AX equals 0. And when exactly do we have a vector whose dot product with itself equals 0? What do we know about the dot products of vectors? Well, let's see. We know that the dot product of AX and itself is equal to the length of AX all squared. And I wonder when we get a vector whose length is, so if its length squared is equal to 0, that means that the vector's length is 0. And what vectors exactly have a length of 0? Well, the only ones I can think of are vectors that are themselves equal to 0. And so that implies that AX itself has to equal the 0 vector. That is the only vector that has a 0 length. And therefore, the vector, that means that X is in, because multiplying A by X gives me 0, that means X is in the null space of A. And I guess I noticed now that I didn't really write the conclusion on the slide. I remember writing this slide a couple of months ago and being so excited about this clever proof that clearly I got so far ahead of myself I forgot to finish the proof. In any case, that's the conclusion. X is in the null space of A, and that means that anything in the null space of A transpose A is in the null space of A. Oh, no, there it is. So that means that lemma 1 said that A had rank n plus 1. Lemma 2 said that the rank of A transpose A is the same as the rank of A, which means the rank of A transpose A has to be n plus 1. And that means that because A transpose A is an n plus 1 by n plus 1 matrix, it has full rank. That means it's invertible. So the only assumption I have to make to answer this question, when is this matrix invertible? The answer is if all of your x coordinates are distinct, then it's invertible, and you're good. So I think we finally put that one on solid ground. And we're ready to finally wrap this odyssey up. So here's a point set, and it contains, and suppose we assume that there is some set of relationships among this data. Suppose now we make what is a more sensible assumption in data science usually, which is to say, before I know anything else, let's start by assuming that maybe there is a linear relationship. So something like that. That is probably not the line of best fit. Let me try again. Let me try and do L2 regression by sight here. Can we find a line of best fit, some linear function that describes the trend being outlined by these points? Well, we now know a lot of different methods for doing that. We could use any of the various LP norms. If we're allowed to do nonlinear programming, we could use like the L7 norm for all I care. But suppose that I take a look at the result with both L1 and L2 regression. And we have both of these. So this is linear regression because we are computing a linear function, and I'm using both the L1 norm and the L2 norm. The L1 norm is the red solid line, and the L2 norm is the green dashed line. Okay, and we see that they're not that different. The set of points is actually relatively clustered around a more or less linear trend, and although it does have enough of a slope that we could have some suspicions, and so both forms of regression are relatively similar. And what I want to basically do at the end here to bring this back to what we were talking about is to consider the fact that in this huge odyssey of derivations that we've done today, we started by talking about means and medians, which is a very simple one-dimensional optimization problem where we discovered that the median is the result of doing what is equivalent to sort of L1 regression, which is to say minimizing the sum of absolute values, whereas the mean, as it turns out, optimizes this function that it could be considered similar to L2 regression, so least squares. And we noticed that the mean is far more sensitive to outliers because of that squared error term, where if you have larger errors, they tend to skew the result disproportionately. And we've now derived these regression schemes for higher dimensional cases, 2 dimensions, 3 dimensions, 4 dimensions, and for polynomials that may not just be linear, but using the same techniques, minimizing absolute values versus minimizing squares. And so obviously many of you came into this course familiar with sort of least squares regression being the default regression mechanism for a lot of different reasons, one of which is you can compute those coefficients using only linear algebra. You don't need to learn linear programming or know anything about optimization or how to use a solver to perform L2 regression. And I mean, it does a good job in most cases. But there is one situation that goes back to that issue at the very beginning where it doesn't. L1 regression is, this is what I just said. L2 regression is sort of analogous to the mean. L1 is sort of analogous to the median. Let's consider what happens if I add an outlier. So here's my data collection. They are clustered pretty close to the line in the grand scheme of things. Suppose I add a big fat outlier right here. And let's take a look at the results. So here is one outlier. It's pretty far out, but we know that when we collect data, we can expect to see outliers sometimes. And certainly depending on the application, if you're a data scientist, you might have to analyze an application to understand when a particular form of outlier might arise. We know they might happen. And suppose I've added this outlier and then run regression again. So the lines shown on this plot are the lines of best fit for the updated data set. Let's take a look by flipping back and forth between slides how it changes. So here is the original data set, all of the valid data, I suppose. And here is the data set with that outlier. Notice how far the L2 regression line jumps. I have added one data point, and I have very significantly changed the character of the least squares regression, of the L2 regression line. Notice also that, sure, the L1 regression line also moves, but it doesn't move very much. And given that I only added 1 point, we don't expect a massive change. The change in the L1 regression line is a lot more tempered, and I think is a lot more proportionate to the actual change I made to the data set. Notice in particular that the L2 regression line now has tons of points above the line because it's had to bend so far down to accommodate the massive squared error term of that one outlier. And so an example of a case where you might, now that you know more than one regression technique, where you might want to be careful about always defaulting to least squares regression is if you know that your data set is prone to containing certain types of outliers, anomalous outliers that may have a large impact on these squared error terms, that's a case where L1 regression might be a better idea. And is, I guess, similar. I would say it is the sort of higher dimensional version, the generalized version of that situation where you can't always trust the mean of a set of data because even one outlier can dramatically affect the mean of a data set. So taking it back to the initial example, when people talk about the average of a midterm or something, there's always this issue where the whole average gets completely skewed if, one person didn't write the exam and got a 0 on it or something. If the average is sitting around 80% and one person in a class of 30 people doesn't write the midterm and gets 0, that could end up dramatically changing and skewing the average, bringing it several points down, even though it's only the contribution of one data point. And so we now have seen ways to compute other regression techniques that aren't as influenced by massive errors. Now, it's also worth considering that L infinity norm, which we didn't talk too much about because it's an assignment problem, that L infinity norm goes in the opposite direction. So it actually takes into account only the most significant outlying data point, which is why it's not, I don't know, as generally useful for regression, although it is still a clever assignment exercise to come up with a way of making a linear program for something that looks sort of strange. So look forward to that.